This is a little OpAmp booster circuit I made, a while back. I mean, most of these circuits I actually made like 2 years ago. I just hadn't tested them. But anyway, this is just to test the principle, of boosting an OpAmp, basically creating a Class D amplifier that doesn't have some of the traps, crossover distortion and trying to get it balanced right and all that, because if you don't get that balanced right, you could have thermal runaway and a bunch of other stuff. I mean, supposedly, this in theory might get around some of that. But at any rate, I built it just, for shits and giggles, and, here's the circuit board I made for it. But, that's the circuit right there. So, I've been testing. I'm driving at 9 volts, but Analog Discovery is basically a voltage follower. So, Analog Discovery won't put up more than, again, like 4.5 volts. So, again, I'll get like 8 or 9 volts peak to peak out of it max anyway. So, there's no reason to drive it at a higher voltage, even though theoretically I could. There's hardly any current right now. I do actually have, like 140 ohm resistor or something like that on it. So, it's got something of a load that I applied. And if you'll notice too, basically this is just going into the raw input of the OpAmp, 741 OpAmp, so it has a low slew rate, and you'll see that in action in a minute. But I don't even actually have a resistor, an input resistor on it, so it's just, I'm just feeding Analog Discovery right into it, which is just fine. And I tried putting one on there, but it doesn't make any real difference. So in this case anyway. But yeah, here's the the waveform. Results. I got a triangle wave I'm driving into it. You can see with a sine wave what it's like, and right now it's always going to be a gain of about 1. So but you can see I'm driving it at the maximum voltage I can get out of the Analog Discovery, because again it's pretty much just a voltage follower, but it does give you a current boost. So right now I had it at 100 hertz because I was kind of curious about putting a 1 microfarad capacitor on it, and it laughed that off at this frequency, but its impedance would be fairly high. It sure as hell wasn't when I first did it at 18 kilohertz. The thing drew 120 milliamps out of it, because it's like 1 ohm, 1.2 ohms, at a higher frequency. So yeah, you could see it struggling a little bit with that. Still took it surprisingly well though, but I wouldn't want to put that on there for too long at 120 milliamps. Even though the circuit in theory could handle it, but it is throwing current out of phase back at the transistors, like I covered in one of my videos. So still reluctant to put it on it, because this is just a little test circuit with TO92 transistors. So, but yeah, you can see as I get the frequency up there. Let's see. It behaves. It has about a, well, in fact, you're going to see here, this is the full power bandwidth to the extent I can drive it, which is, again, plus or, 4 volt, 4.5 volts peak or so, times 2, but, I got up to 4 kilohertz right now, and 6 kilohertz or 13 kilohertz, and let me change the scale here. Okay, so you're starting to definitely see some distortion, in the sine wave at this voltage, at 19 kilohertz. So let me take it down here, but yeah, right about, you got quite a bit of distortion there still, but still starting to look like a sine wave at 13 kilohertz. Yeah, still got some pretty good distortion in there. That's the wrong damn direction. Okay, it doesn't look too bad at this point. Certainly at 9 kilohertz, you know, it's all right, but you are starting to get some distortion at 11 or 12, even though there's almost certainly still some here too, but, you go up to 20 or 30 kilohertz, that's what you get. But yeah, if you keep it around 9 or 10 or so, it's not too bad. It's at 8 kilohertz right now, but still maintaining its voltage quite nicely. Now if we switch over to a square wave, you can see the slew rate playing games with you, trapezoid wave, actually looks pretty good. So, that's rising, I guess, slower than its slew rate. Triangle wave is like perfect. We're nowhere near that. In fact, let's see how long it takes us to get distortion on a triangle wave. See, we're starting to see a diminution in output now. We're at about 14 kilohertz right now. So, that's probably coming close to matching the slew rate. The square wave looks really fucked up, but, like I said, sine wave is quite distorted. Power sine, same kind of thing. A triangle or ramp wave, yeah, it doesn't look like a sawtooth. There's the noise thing, pulse, yeah. So, but like I said, as far as high power, I mean, you get higher frequency out of it at lower voltage levels. Like, let's go back to the square wave anyway. Hold on, yeah. Go back to the square wave and let me lower the voltage. So I'm down to 3 volts peak to peak, or not 3 volts peak to peak, but 4 volts ish peak to peak right now. So I cut the output in half basically. But yeah, you still see evidence of plenty of distortion, at 14 kilohertz, but that's to be expected, because you're going to have slew rate issues here no matter what frequency you're at. I think this OpAmp, by my calculations, only works at about, it's supposed to be half a volt per microsecond, but I think it's more like at about 330 millivolts per microsecond. But anyway, going back to a sine wave, up the frequency, yeah, it's quite distorted there. But yeah, we can do maybe 24 kilohertz with it at half that voltage. So, it's got, like I said, a little, dip right there in it, so it's got some distortion, but visually, anyway, it doesn't look too bad at that frequency. And, at 16 kilohertz, it looks halfway decent. So anyway, it's square wave still looks like a trapezoid, but that's gonna happen. That's a slew rate issue right there. So again, if you wanted to, get it up to a higher frequency, you need a higher slew rate OpAmp. There's nothing you can do about that. So anyway, I just wanted to show you that, and because it's still a neat little principle. I'd like to actually try to use that sometime when I need to amplify some kind of waveform or something. Like, it would be nice to have a frickin' amplifier for the analog discovery, right? So you get not only higher voltage but higher current waveforms. But this certainly wouldn't have the frequency response you want, and it would probably be really difficult to get much of a frequency response. But shit, even get up to, high fidelity, or reasonable fidelity at, 50 kilohertz or so. Hell, that's an improvement for a lot of things. But you need a slew rate, probably about 15 volts per microsecond at the, I would say, it's isn't too expensive of an OpAmp. Some NE 5532s are, somewhere like 10 volts per microsecond or so. But anyway, it's it certainly warrants some further exploration later on. So, and if you wanted to run, say I did run a network analysis on it before, and I got this kind of behavior, so you can see that, as far as that's concerned, we had basically unity gain you know, out till about, you know, it was saying about 40 kilohertz. So I doubt that's undistorted, but I did only throw a 1 volt signal at it, so, you know, and you can see what its, you know, roll off is. So like I said, it's not the signal. You know, the blue line is the input signal. It doesn't actually go that high, so I still haven't figured out what that's all about yet. You know, so if you take it up to 20 times gain, you know, it looks like the signal's going through the stratosphere. But it's not, you know. That's why I was testing it at much higher frequencies to see if that's true, and it's not the signal that's doing that, so it's just the software program that does that for some reason. So, anyway, just thought I would share that with you. Cheers. Oh.